Okay, so what we're going to talk about here is the method of exhaustion. There's quite a bit to look at here, but I'll try to break this down simply. The method of exhaustion is a way to get closer and closer to the circumference of a circle. But how exactly do we discover that it's irrational? I won't get into how they discover or the amount of mathematics required to get to irrational numbers, but it's just a very long exercise. But basically, to keep it simple here, we have a circle. We have a square inside the circle. And the square has the same diameter as the circle. So if we take this and we join all the corners, we have each length here is the hypotenuse. And if we consider this as 1, this can be considered, so we have a magnitude of 1. And then right here the hypotenuse would be considered the square root of 2. Irrational numbers, anything other than a perfect square is an irrational number. So, for example, a perfect square would be the square root of 9 is 3, but the square root of 2 is an irrational number. And there's nothing really too special about them. Say, for example, 12 divided by 6 equals 2. The square root of 12 divided by the square root of 6 equals the square root of 2. So they're quite common, but when we deal with irrational numbers, when we divide them, that number is also irrational. And when we deal with the method of exhaustion, as soon as we divide an irrational area, we're going to end up with, so right here, if we have the square root of 2, and we divide that in half, we have half of the square root of 2. And if we apply that to the hypotenuse, if we use in trigonometry, if you use the cos function to solve for the hypotenuse, we would take the square root of 2 divided by 2 divided by the cos of 22.5 degrees, which will give us, so here we have an irrational base, and we have an irrational hypotenuse. And if we keep with the method provided here, this will become the base, which is irrational, and then again we will just apply that to hypotenuse, and this irrational measurement will just continue on and on and on until we get to the circumference. So we take this segment, divide it into 2. We have a right angle. And then if we take this and we join the points, we have, at this point now, we have this triangle right here, which is represented in the blue. And if we take this triangle and cut it in half, we can solve for these angles, because if we know this is a 45, or right here, we got a 45, we have a 45. Here, we still have, we cut this in half, this is 90 degrees, this is still even, so we have a 45 degree and a 45 degree. Now once we start chopping that apart, we're just going to keep splitting the angles in half, but sort of how do we know what the angles are? So we have, if we take this triangle, so we've taken this first triangle, split it in half, joined points. And now we have this triangle and this triangle here, which can be represented by just this one right here. So we know that right in here, this is a 45 degree angle. And we've taken this triangle and we've split it right in 2. So we know that if we take, so right at the base, we're at the halfway point, we run a line perpendicular, And now we have 22 and a half and 22 and a half. And if we know this is 22 and a half, all degrees in a triangle are going to add up to two right angles, otherwise known as 180 degrees. So if this is 22 and a half, this is 90, well that means that this has to be 67 and a half degrees. Which means that since we have a right angle here, this is 67 and a half, this also has to be 22 and a half degrees. And this whole method is going to just keep on. So if we take this, we've split it in half, join the points. Now we have this green, these two green triangle segments right here. So we have the first right in here, and we have the second right in here. And then each degree is just going to be split in half. So we have got the 45, take that in half, 22 and a half. Take that in half, 11.25. And every time we make this division, the angle will divide evenly right along with it. So we're going to go from 4 sides to 8 sides to 16 sides to 32 sides. Now as far as drawing this, it's going to get a little hard to draw. So right around this point we'd have to just do the math on the whole perimeter, add up each hypotenuse, because that's basically what we're doing. Each hypotenuse is being added up here. We don't need to add up each individual one, but as we solve, if this gets to 64 sides or however many sides we're going to just add up each one of those pieces and get slower and slowly approximate closer to the circumference. So we find that if we just take a radius of 1, so the circumference is 2 pi r, so 2 times 1, or 2 times the radius times pi, otherwise known as 2 pi r. 2 times 1 times pi gives us 6.28 for the circumference. And if we have a 16-sided, so just as we would have here, so we got 4, 8, and 16 would be expressed as in the green, we would get an approximation. So this is with pi, right, with pi as we know it. So 16 sides for each hypotenuse would be 0.3901 continued. So that would be this green segment right here would be 0.3901 continued, and we would multiply that by 16. You can see we would approximate, we're getting pretty close already, 6.28, so 6.24. And then if we went with the next round, it would just get closer and closer and closer to the number that we know now as pi. So that's just a little, for instance, on how one of the ancient methods of calculating for the area of the circle. So if we just sort of take off of that, now if we take a circle, we slice it in half, we would have a bunch of little rings that we can make around the circle. And then those little rings would add up, and each ring would be just a little more, a little more, a little more, until the base of this triangle would be the circumference. So that would be 2 times radius times pi, or 2 pi r. And you have the radius. So the area of, now if we multiply this, we would have 2 pi r times r. So the rectangle area would be 2 pi r times r, otherwise known as 2 pi r squared. But the area of a triangle is half of the area of a square, or in this case a rectangle. So the area of a triangle is 1/2 the area of a square, or like a triangle or rectangle in this case. So the area of the triangle is 1/2 2 pi r, which means the area of the circle is pi r squared. And that's typically how we know the area of a circle to be. So we'll deal with surface area, volume, and all that kind of thing. But just to take this into the next part of it, we were talking about area equals diameter squared for conductors. That is unit 11 in our Delmar's book. So I've provided you with a link. You could read up a little more on it. But here we have, if we have a diameter of 1, is 1 mil. So, which is 1/1000th of an inch. So if we just take the radius at 0.5, so we have a diameter of 1, which would be 1 circular mil, and again, review your unit 11 there. The area of the square, so if we just took this again, 2 times the radius times pi times 0.5 gives us 1.5707. So the area of a circle is going to be 1/2 that, which is 0.7853, yada yada, which would be also the area of the triangle. So what you'll find in that link, they talk about the area of a square mil and the area of a circular mil. So if we take 1 mil squared, so the diameter of a circle is 1 mil. This diameter equals 1/1000th of an inch. If we take a square mil, so this diameter, and we square it, 1 mil times 1 mil, you got 1 square mil. So you got 1 mil square. So basically what we're looking at here is the area of the circle, so 0.7853, yada yada. So the ratio of 1 mil squared to the circular mil is 1.2732. And that's what you'll find in that handout, is that this, between the two, the ratio, or basically here, the ratio of 1 square mil to 0.785, yada yada, so it's 1.2732, blah blah blah, times larger. And that's what you're looking at in that link I provided you. And that'll be it for today. So just work on the assignments provided you in CAMS, and I'm gonna now just keep the math coming.